Hello everybody, I am Seppälä. This recording is a preparation for a talk which I'm going to give tomorrow, 24th of June 2013, at a meeting organized in the honor of Emilio Bujalance in Linköping at the University of Linköping. The topic of the meeting is Riemann surfaces and their symmetries. Now, the topic of my talk is Riemann surfaces, quadratic differentials, and MOOCs. Everybody attending this meeting knows what a Riemann surface is. Most people also know what a quadratic differential is, but almost nobody knows what a MOOC is. MOOC is short for Massive Open Online Course. MOOCs are in the process of making a big revolution in instruction. A mathematical model for MOOCs can be built in the language of Riemann surfaces, and this will be the bottom line of this talk. But let me first start by observing that tuition in the US has gone up a lot. From 1980 to 81 to the academic year 2010-11, the tuition has practically doubled. This is adjusted for inflation and in 2010 dollars. This table comes from Department of Education, so this should be pretty reliable. Education is getting more expensive, and this is true also in Europe. Something needs to be done about this, and my solution is to industrialize instruction. A lot can be done using technology. This is a screenshot of the WEPS, World Education Portal's website. This is my solution to this increasing cost of instruction. This is a free web service that offers content and services to run online courses. University of Helsinki is offering several online courses which students can take for credit. Texas A&M University, Florida State University, Aalto University, and 12 other universities are using this service. WEPS massive open online courses, WEPS MOOCs, can be used to teach 1,000 or more students with the same effort as what it takes to teach 10 students. The system gives adaptive individual support to students. This support that the online students get is usually better than what the students of a traditional face-to-face class can get. At the University of Helsinki, we developed an online calculus course, and that was offered along with a traditional calculus course. Topics treated were the same, examinations were the same, and examinations of the online course were done in the traditional way. They were proctored written examinations. Students took them at the same time as what the students of the traditional courses took the examinations. This was in fall of 2011, and the result was that the grade average of online students was 20% higher than that of the traditional students. This is one whole letter grade higher. The WEPS instructional model works. The lectures in these online courses, they are short 10 to 15 minute long YouTube videos. They explain one method or result. They come with sets of solved problems, which are typically 5 to 15 minute long YouTube videos, and all these materials are presented as videos, but they come with PDF files, so students can print the PDF files, use them to take notes or discuss these topics. Then there are exercises which help students to master the topics of the course. And then there is assessment that informs the system what topics students have mastered and what not. Topics of central importance are treated at different levels. There's a gentle introductory treatment, there's a normal, this is the aim of mastery of the course, and then there's a rigorous, this is for the select few who want to learn more of these topics. There are peer-reviewed workshops. In peer-reviewed workshops, students solve given set of problems, submit their solutions, and after the submission deadline is over, they get a model solution and instruction to review solutions of 5 other students. These peer-reviewed workshops have turned out to be a very powerful instructional tool. And all this is accompanied by discussion forums. Discussion forums are places where students can also offer peer instruction. So there's a peer review, there's peer instruction, and this use of peer review and peer instruction makes these courses scale very well. They also force students to learn very well if students remain active here. Here is a screenshot of one gentle discussion of a topic. There is a video, limits of functions, there's a handout, there are PDF files of slides, slideshow, there are solved problems, there's a handout, there are limits 1, which is practice and assessment, limits 1 for practice, no extra credit, limits 2 for practice, no extra credit. These limits 1, limits 2, they are quizzes that support students and to master the topics discussed. WEPS stack quizzes pose students problems to solve. These problems can be used to practice and they can be used to assess students' mastery of a topic. Here is a sample question. Integrate e to the negative 3x with respect to x. This is a typical stack question that depends on a parameter. This parameter is negative 3. When the student takes this particular quiz again, he gets a similar question, but then in place of negative 3, there will be another number. Students have to solve this on the manually, solving this on a paper, and then by writing the solution in the box indicated. And now here is what a student might start writing e, negative e, and then caret for exponentiation, opening parentheses negative 3x, and so on. When students write this, the system monitors what the student is doing and gives support to the student. So here the system has told the student that his or her last answer was interpreted as e caret opening parenthesis negative 3x and that this answer is invalid. You have a missing right bracket in the expression negative e caret opening bracket negative 3x. And the brackets are incorrectly nested in this expression. You seem to be missing the multiplication character star. Perhaps you meant to type negative e to e caret opening parenthesis negative 3 star x and so on. The system holds the hands of students as they type in the answers in this box indicated. This holding the hand of a student is completely automatic and happens without the student having to invoke an additional feature. So the student adds this multiplication character and closing bracket and then realizes that he still needs to add the constant of integration, so the student writes plus, and when the student has written the plus, the system tells the student that the last answer was interpreted as e caret opening parenthesis negative 3 star x closing parenthesis plus, and that this answer is invalid because the plus must be followed by something. and it must be followed in this case by constant of integration, so I write c. And now the answer was interpreted as negative e to the power negative 3x plus c. And maybe this is what I want to present as my solution. So I submit this for grading and I get the feedback that this is an incorrect answer. I forgot to deal with this negative 3 in the exponent. And then I can learn from the feedback what went wrong. And I can take the quiz again. If I did not get it right, I can learn how to solve this question from the feedback that the system gives. The system gives feedback which is particular to the problem that is being discussed. The feedback is a solution of the problem. So next time the student takes the same quiz, he gets the problem integrate e to the negative 5x with respect to x, so the student cannot copy the answer of the previous problem, he must learn the method. So this is how WEPS stack works. Students like to practice with these quizzes. Here you see a screenshot of a record of students taking stack quizzes. You see that students have taken them 6, 9, 3, 6, 8, 5, 8, 11, 19, 11, 15, 16, and so forth times. In average, students typically take these quizzes more than 10 times. There is no other way of making them practice so much. Solving problems becomes a game. Students want to get everything right. They solve a large number of problems and they learn. These stack quizzes are part of the content which is offered as a free resource for everybody. So you can use these quizzes within this WEPS system. You can build your own class, you can use this in your own instruction, and you can use these resources in your own classes. You can edit them further and create new classes. All this is available at myweps.com. Here is a screenshot of WEPS Calculus MOOC. This contains a wealth of resources. There are lectures, there are solved problems, there are exercises, there are workshops, there are discussion forums, there's peer review, there's a peer instruction, and then there is a calendar that helps to keep students working under a schedule of the course. Here you see a screenshot of limits of functions treated gently and treated at a normal way, at a normal level. These resources contain quizzes that help students to master, workshops, videos, video lectures, and solve problems. All this wealth of information can be a little bit intimidating. Students' progress is measured by quizzes that they take. And quizzes may result to students dropping out, or they advance from quiz to quiz, and eventually, starting with the diagnostic test, they advance and finish the course successfully by taking the final examination. The use of resources determines study paths. There will be thousands of study paths in a large MOOC. A study path which is appropriate to a particular student depends on the cognitive profile of the student. If the student is blind, for example, that is a severe cognitive limitation, and that student will focus on audio materials, for example. There are other cognitive limitations which may be just as severe as being blind, but may be less obvious. The system will try to figure out what the cognitive limitations of students are by keeping track of what they are doing. The wealth of resources may look overwhelming. Students see lots of materials, there are videos, lectures, solve problems, discussion forums, exercises, peer instruction and peer review and so forth. And the way of using these resources may at first overwhelm a student. Here is a schematic representation of a course. There's a diagnostic test on the left. Students take that when they enter the course. And then there are quizzes. In this case, there are two sets of parallel quizzes. There's a quiz 1, quiz 2, quiz 3, quiz 4, and then eventually a final examination. The red dots indicate that students are dropping out. In this schematic model, the study paths are edges, and the quizzes and diagnostic test dropping out and the final examination, they are vertices of this graph. So this graph is the mathematical model of this MOOC, but this can be improved. We can look at a fraction of the MOOC and we can thicken the edges, and when we do that, we get a Riemann surface. Thickening the edges, the study paths, and the nodes yields a Riemann surface. So now we have a Riemann surface model of a MOOC, and the flow of student defines a metric on this Riemann surface. In this metric, the study paths are straight Euclidean cylinders. The length of a study path is determined by the number of resources used in the study path, and the width of the cylinder is determined by the number of students choosing that particular study path. The large blue dots indicate quizzes, and the red smaller dot indicates students dropping out. So here you see a fraction of a MOOC, just 2 quizzes and some students dropping out. The flow of students on a course, of course, depends on the facilitator of the course. The facilitator, the professor, the instructor, or the coach will interact with students and make recommendations, and using those recommendations, students choose a study path which they think is best for them, and depending on the instructor, they may choose a different study path. So the instructor somehow determines and can change the metric of this on this Riemann surface. So in this model, the metric is defined by a quadratic differential, and MOOC is a Riemann surface. Facilitator, instructor, professor, or coach is a quadratic differential on this Riemann surface. This is the mathematical model for MOOCs. Here you see a universal record of the use of resources of a course. When large numbers of students study using a MOOC, they use resources in various ways, and this table keeps simply track on all the use of these resources. It goes on. There are videos, there are PDF files, there are stack questions, there are workshops, and so on. So these numbers define the metric on this Riemann surface model for this particular MOOC. And then we filter the activity reports to find the best study paths for individual students. Remember, we have cognitive profiling of students. We filter the activity reports through these cognitive profiles and then through the success of the students. And we get a recommendation for an individual student as to how to ace this course in the best possible way. So the WEPS Study Navigator will help students to reach their educational goals in the best possible way. This is automatic guidance based on the massive log data collected by the system. Some cars today offer relevant information to the driver projected on the windshield. This is called heads-up display. The driver will see, for example, the current speed limit, the speed of the car, and navigational instructions projected in an elegant way on the windshield. So the driver does not need to take his or her focus away from the road. This is very convenient. It really helps a lot, and once you have such a car, you want to use such a facility always. In the same way, the WEPS study navigation system helps students to achieve their goals and does that in a very discreet way. The development of these methods and these systems are part of the NSF Academy of Finland collaborative work. Here in this NSF press release, this is entitled International Team Targets Innovations in STEM Learning. Advancing an online project in the assessment and effective teaching of calculus is a project supported by the National Science Foundation and by the Academy of Finland. It's being run at George Mason University, University of Helsinki, Florida State University, Texas A&M University, and at Northwestern University. Researchers from the US and Finland are conducting groundbreaking analysis on a massive open online course on calculus that is based at the University of Helsinki, the World Education Portals service. MOOCs represents a potentially revolutionary development in the design of teaching and learning environments. This project involves several universities in the US and Finland. It is conveying a variety of experts on learning, assessment, cognitive diagnostic modeling, and research methodology to advance the learning of calculus and to recommend best practices on the design, deployment, and analysis of this and other MOOCs. This is what we are doing. And this is a service being offered for you as a free service on the WEPS site. Let me now return to the slide that you already have seen. Tuition in the US educational institutes has gone up a lot during the last several decades. How is this possible, one might wonder? We are teaching in the same way as we always did. Our salaries have not gone up so dramatically as to justify this table. So, from the point of view of a college professor, it is hard to understand why the cost of tuition goes up. And the cost of tuition goes up because the cost of other activities in the society have gone down. It is not that education has become more expensive, it is that other activities have become less expensive. Logistics, to start with, uses information technology in a very efficient way. Banking, manufacturing, insurances, and so forth. Everywhere information technology has been used to streamline processes and to make the system work in a more effective way. This has not happened in education. It needs to happen in education now, and what we are proposing by WEPS is one way of doing that. The Road Not Taken, Robert Frost, from 1920. I shall be telling this with a sigh. Somewhere, ages and ages hence, two roads diverge in a wood, and I took the one less traveled by, and that has made all the difference. Now I invite you to join me in this road less traveled by. Thank you for your attention.